Imagine a particle that defies the cosmic speed limit, moving faster than light. This concept might seem like pure science fiction, but it's a real and fascinating result of some physical models. The debate on whether these hypothetical tachyons are compatible with the theory of relativity and whether they can be described using quantum field theories has been ongoing among experts. Recent breakthroughs have introduced a groundbreaking solution to this dilemma, offering fresh material for scholarly discussion. The question arises, how can tachyons, particles that theoretically exceed the speed of light, be understood? What challenges do they present for researchers, and could they potentially help solve the elusive mystery of dark matter? At first glance, one might assume that the laws of physics are straightforward: all bodies with mass attract each other, objects fall towards the center of the Earth, and nothing can exceed the speed of light. However, the world of physics holds a more complex picture. Hypothetical particles, termed tachyons, are theorized to race through space at faster-than-light speeds and could even travel backward in time. Initially, these extraordinary properties seem to belong to the realm of science fiction, such as in Star Wars, given their stark contradiction to Einstein's special theory of relativity. According to relativity, nothing can surpass the speed of light, approximately 300,000 kilometers per second, 1.08 billion kilometers per hour, and even massless particles like photons cannot exceed this limit. Despite these constraints, theoretical loopholes exist that may allow particles to travel faster than light. In 1962, several physicists highlighted that while the special theory of relativity accommodates normal matter moving at sublight speeds, it also permits solutions where particles could theoretically move at superluminal speeds. American physicist Gerald Feinberg categorized these particles in 1967 with terms based on their characteristics: tardons, which always move slower than light; luxons, which travel at the speed of light; and tachyons, which move faster than light. While the term tachyon gained prominence, it remains a topic of theoretical debate. Though tachyons provide a mathematical solution within the framework of special relativity, their existence is not confirmed. For tachyons to exist, their square mass must be negative, a notion that theoretically allows them to exceed the speed of light. This is feasible because, unlike normal particles, tachyons would lose mass and energy as their speed increases. Consequently, an infinite amount of energy would be required to slow them down to or below the speed of light. Feinberg proposed that tachyons could be created through a mechanism similar to the Higgs boson, where they arise from the spontaneous symmetry breaking of a scalar field in the cosmos. This interaction might involve dark energy, which is thought to contribute to the universe's expansion. Puss's team suggests that the previous framework for tachyons was too restrictive, failing to account for their unique properties. Tachyons theoretically move in a different time frame, potentially traveling backward in time. Thus, the models must consider both initial and final states, expanding the Hilbert space. This adjustment challenges our understanding of causality, as it implies effects could precede their causes. The extension of Hilbert space might resolve the previous issues by providing a mathematically coherent framework that integrates tachyons into quantum field theory. In addition to these theoretical advancements, the insertion of tachyons into quantum field theory could illuminate some of the mysteries surrounding the Higgs boson and the origin of its quantum field. Puss's findings might shed light on the dynamics of phase transitions, although their practical implications remain to be fully explored. Despite these promising developments, not all researchers are convinced. Critics, such as Kaf Yossi from the Institute of Fundamental Research in Seoul, argue that the proposed theory violates fundamental principles like locality and introduces unphysical behaviors. Yossi maintains that the idea of tachyons, and their associated problems, might reflect misconceptions rather than genuine physical phenomena. While the existence of tachyons remains a contentious issue, their potential role in explaining dark matter and dark energy is intriguing. Dark matter, inferred from its gravitational effects on visible matter, remains invisible and undetectable by electromagnetic radiation. Tachyons might offer an explanation for this elusive matter, as well as for dark energy, which is responsible for the accelerated expansion of the universe. Recent studies suggest that tachyons could account for both dark matter and dark energy. A tachyon cosmology model, when compared with observations of type Ia supernovae, standard candles for measuring cosmic distances, matches the data as well as the current cosmological model. This model could provide a unified explanation for phenomena attributed to dark matter and dark energy. However, empirical proof of tachyons is still lacking, and the practical implications of their existence could introduce new challenges, particularly regarding the nature of time and causality. In summary, while tachyons continue to spark debate and exploration, their theoretical framework has advanced significantly. Researchers are working to address fundamental problems and determine whether these superluminal particles could provide answers to some of the universe's greatest mysteries. As the scientific community continues to investigate, the possibility of tachyons becoming a cornerstone of our understanding of the cosmos remains an exciting frontier in physics. The idea of tachyons emerged from theoretical physics as a result of exploring the fundamental limits of the universe. These particles, if they exist, are theorized to travel faster than the speed of light. This concept fundamentally challenges Einstein's theory of relativity, which posits that nothing can move faster than light in a vacuum. According to relativity, the speed of light is a universal constant, approximately 300,000 km per second, 1.08 billion km per hour, and acts as a cosmic speed limit. Photons, the particles of light, are massless and travel at this maximum speed, reinforcing the idea that this limit is absolute. However, theoretical physics has always been a domain rich with paradoxes and exceptions. The concept of tachyons, particles that are theorized to travel faster than light, challenges our conventional understanding. Tachyons were first proposed as a mathematical solution to the equations of special relativity in the early 20th century. According to Einstein's theory, as objects approach the speed of light, their mass effectively becomes infinite, making it impossible for anything with mass to reach, let alone exceed, this limit. Yet, tachyons are posited to always travel faster than light, defying this constraint. The notion of tachyons is rooted in a theoretical loophole in special relativity. In 1962, physicists identified that while special relativity accommodates solutions for particles moving at sublight speeds, it also permits other solutions where particles could theoretically exceed the speed of light. In 1967, American physicist Gerald Feinberg introduced the term tachyon to describe these faster-than-light particles. Feinberg categorized particles based on their speed relative to light: tardons, always slower than light; luxons, always at the speed of light; and tachyons, always faster than light. Although tachyons gained prominence as a theoretical concept, their physical existence remains a topic of considerable debate. The concept of tachyons hinges on the idea that these particles would possess a negative square mass. In conventional physics, negative mass is a theoretical construct with problematic implications. For tachyons, this negative mass would theoretically allow them to exceed the speed of light. As these particles approach or exceed this speed, they would lose mass and energy, creating a unique situation where slowing them down to light speed or below would require an infinite amount of energy. Feinberg's proposal suggested that tachyons could be created through mechanisms analogous to the Higgs boson, arising from the spontaneous symmetry breaking of a scalar field present in the universe. This field interacts with matter and might even play a role in the formation of dark energy, a mysterious force responsible for the accelerated expansion of the universe. In addition to resolving theoretical issues, the inclusion of tachyons into quantum field theory could provide new insights into some of the universe's most profound mysteries. For instance, the findings might shed light on the Higgs boson and the origin of its quantum field. The dynamics of phase transitions related to the Higgs boson remain a significant area of inquiry, and tachyons might offer a new perspective on these processes. Despite these promising developments, not all researchers are convinced by the proposed models. Critics, such as Kof Yossi from the Institute of Fundamental Research in Seoul, argue that the theory of tachyons might violate fundamental principles such as locality. Yossi contends that the proposed theory introduces unphysical behaviors and may not accurately reflect the true nature of tachyons. According to Yossi, the concept of tachyons with negative square mass could be an artifact of theoretical misinterpretation rather than a real physical phenomenon. The debate over tachyons extends beyond theoretical considerations into practical implications, particularly concerning the nature of dark matter and dark energy. Dark matter, an invisible form of matter inferred from its gravitational effects, is postulated to explain the movements of visible matter in the universe. Dark energy, on the other hand, is thought to drive the accelerated expansion of the cosmos. So, while tachyons remain a theoretical concept and their existence is still debated, the latest research is pushing the boundaries of our understanding. Whether they can truly exceed the speed of light or help solve the mysteries of dark matter and dark energy remains to be seen. Stay tuned as scientists continue to explore these cosmic enigmas, and don't forget to like, subscribe, and hit the notification bell to keep up with the latest discoveries.